Okay, so the deal here was, why does the ratio test work? Why are those the situations that lead to convergent and divergent? This is more of a motivation than an actual proof, but let's take a look here. What we do for the ratio test is we kind of lean on the idea of the geometric series. And what we know about the geometric series is that if the R value is less than 1, we get a convergent series. And if the R value is greater than or equal to 1, we get the divergent series. And it's this idea that plays into the ratio test, because if you think of the ratio test, if the limit of the ratio is less than 1, that's when we get convergent. And if the limit of the ratio is greater than 1, we get divergent. The only difference here is the equals 1. It's a little hard to know which way it goes. We say inconclusive. What's really happening here, and this may be a little bit much to look at, but, well, it's a video, so you can pause it, is that we're looking at the ratio of some term divided by the previous term, but we're just not looking at it anywhere. We're looking at what happens to this ratio as you move further and further and further down the series. Not just the second term over the first, or the 12th divided by the 11th, but even the 500th term divided by the 499th term. And what we are looking at is this ratio is really what would you multiply the term by to get to the next term. So what do you multiply a sub k by to get to a sub k plus 1? That's this ratio. And that's the common ratio that we talked about with geometric series. It's not common in this case, or these more general cases, because that ratio might change. But if the ratio has a kind of limiting value, that's when we're going to be dealing with convergence or divergence. So it may not be a geometric series, but it starts to act more and more like a geometric series. And that's why we can draw the conclusions that we draw. So in a true geometric series, like 1/2 to the k, we can recognize that no matter which terms we take, we keep multiplying by a half every time. Even all the way out here, we keep multiplying by a half. The ratio is 1/2, that's less than 1, and so it converges. When you have something different, like k over 2 to the k, our series now looks like this. But if we start taking ratios of terms, what we find is that the ratios, while all different, the ratios approach 1/2. You can just take any pair of them and you keep doing it, and your ratio is getting closer and closer to 0.5. All that means is that the further along you go in this series, the more it begins to act like a geometric series with a ratio of 1/2. And just like the geometric series ratio half, it's convergent. It's this idea that basically sets the stage for the ratio test to work the way it does. It's not a proof, but it does offer a little bit of an explanation as to why the conclusions are what they are. So I think we're going to stop there, and I think we may be done with ratio. I may give a few problems more off to take a look, but there's one topic left of new material. We are going to get it this week. I'll probably stretch it out over a few extra days because we've got various holidays and whatnot coming up this week. But I would like to get through the last topic so that then we can start full review. Because that AP test, I'm not sure what date we're going to pick, but we have to work on the idea that we're going to be on May 12th, Tuesday, May 12th. So that's what we're looking for. We got to get to review. One topic left.